Hi, I'm Zach, CT of Mach9, and so I'm going to talk about this. It works? Cool. I'm going to talk about this. I'm going to talk about this sort of intriguing title on how to create the ChatGPT moment in 3D. What is the ChatGPT moment? We'll get to that. But first, I want to talk about the 3D part. So at Mach9, we're automating geospatial intelligence. Our job, our company, is focused around making the best maps to accelerate the development of all global infrastructure. We're a growing team of 22 people. We're based in San Francisco, a couple blocks down the road. We're previously from all of these different companies. That's our beautiful faces. I'm up there. But to talk more about what we do, I want to start with what is a map and why do you care? Everything around you, whether that's a building or a road or the chairs you're sitting on, is designed and built, and the designers always start with a map. Understanding the environment of what you're building is crucially important to designing it. So if you're building a road, you have to understand the topography of the area that you want to build the road in so you know where to move dirt around. If you're building a building, you have to understand the site plan to know where to pour your foundation, where to build your walls, where to build your ceilings and doors and windows. And so maps are crucially important across the entire life cycle of a built asset. In the planning and design stage, this is typically with a survey. So whenever you're building something, doing construction, you start with a map of the area. While you're building the building or the road, it's important to make sure that you're building the right thing. Contractors build buildings based off of blueprints, which are their own versions of maps. And nowadays, they typically use digital versions of blueprints called BIM models to check and make sure that they're building the right thing at every single step of the process. Once you've built the thing, you have to maintain it. And to maintain something, you have to know what it's supposed to look like. So asset inventory is understanding what out there in the real world do you own is crucially important for making sure that everything works smoothly. For example, if you're the California Department of Transportation, you're responsible for making sure that all the stop signs are there in the right place with the right condition. And so you have to go out every 2 to 4 years and check to make sure that all the stop signs are working well. So map making is this massive industry. It's essential for any organization that interacts with the physical world. So there's just millions of jobs that are related to maps. Whether you're a surveyor or a CAD technician or a traffic engineer or an urban planner, you're crucially working with or creating these maps. So how do you actually create a map? Well, the first step to creating a map is to understand all the measurements of the real world. So this is the job of a land surveyor. On the left, you can see a couple of land surveyors doing what we call traditional surveying with an equipment known as a theodolite, which measures basically angles and distances. So if you remember back to middle school or whenever you took geometry, trigonometry is very, very important for these guys. And probably some of your math textbook trig problems were related to surveying. Once you have all the measurements, you can then map out the relationship between different features in the real world to actually plot it. So on the right, you see an example of sort of plotting a river course by measuring the distance from the river course to a bunch of different spikes that have been placed in the ground. And so that way you can actually plot out the course of the river. And so this would be helpful, for example, when you're doing a flood analysis and you need to know the exact spot of the riverbed. But when you have all your measurements, converting those measurements to a map is a very, very manual process. This is the job of what's called a drafter, and it's incredibly slow. What we've been seeing in the surveying space, the process of creating a map, is that there's a new way to collect measurements. So maybe 30 years ago, every single survey was done with these theodolites. It's called a traditional surveying method. And to take all the measurements needed to create a map of an area took like 100 hours per mile of roadway, for example, that you're mapping. And it's out in the field, in the sun, in the snow, in the sleet, in the rain. Really horrible working conditions. Actually, I think a lot of them get hit by cars. It's really bad. Very dangerous. And so over the last 20 years, we've seen a lot of adoption of this new technology. It's called a mobile mapping system. It's a LiDAR point cloud sort of sensor plus a camera. You mount it to the back of a truck and you just drive through the whole area. You can collect all your measurements with this basically at road speed, like 30 miles an hour. And you get this beautiful point cloud of the whole area. It's like millimeter precise. So you can go ahead, you now have all your measurements that you have to do, but you still have to convert this to a map, right? And that is still incredibly slow. So even though you can drive through an area and collect all the measurements that you want at 30 miles an hour, it still takes hours to days per mile to actually trace out the relevant features from that point cloud. It's still incredibly slow. It's in a back office, you get the air conditioning, but it still takes a lot of time, and it's actually a big part of the cost of like a typical construction. Like your typical construction will spend 1 to 2% of its like total budget on land surveying. So at Mach 9, we solved the second problem. So here you can see a project that we worked on where you see first the point cloud that was collected with the mobile mapping system, and then all of the lines that we automatically predicted and analyzed to create the map. We are creating maps directly from these sensing systems without any sort of human intervention. So that way you can actually use these large mobile mapping systems in an effective way. So on the left, you can see sort of the initial starter data. And then on the right, you see our results. We're creating these maps automatically from the point cloud. Simple kind of concept, requires a lot of machine learning on the back end to power it. Requires a lot of understanding of how to process, because these data sets can be hundreds of miles long. They could be like terabytes and terabytes, so how do you even stuff this thing into a model? It requires a lot of sort of very advanced machine learning techniques. But here you can see sort of another shot of a different area of the data set that we mapped. And so we are providing hundreds to thousands of dollars of value per mile that we create these maps on. There's tens of thousands to hundreds of thousands of miles of surveying out there. So that's what Mach 9 does. But I think that we wanted to get to sort of where does this sort of ChatGPT moment come in? And that's what I want to talk about for the second half of this presentation. But to explain where I'm coming from, I want to talk through a brief history of what I think of like the last 15 years of machine learning has been. So I think that it's about more data plus more labels. And then what that translates to is that you can now create new model architectures that can take advantage of all that data, which ultimately gives you new capabilities, not just in like a quantitative, oh, my model metric scores are going up kind of sense, but in a qualitative, I can solve challenges that I could never before kind of step. And roughly from like a tech background side, this is because the amount of data that you have not only determines how good your model can get, but it determines what size of model is best for that amount of data. In the large language model world, this is commonly called the chinchilla scaling law, but it generalizes to basically any machine learning task. And so you see that sort of on small data sets, smaller models perform the best. Over on the left-hand side, that blue curve on the left-hand side is the smallest model architecture, and it performs the best at low amounts of data. But what that small model cannot do is it cannot generalize to larger data sets. It has a sort of lower bound beyond which it cannot grow. Versus if you have a much larger model, you can learn more. So let's walk through a couple of case studies of this phenomena happening. So first, we'll talk about 2D imagery. So the basic question here is, in 2014, 2D image understanding, just like a normal image, was so hard that this is a relevant XKCD. And it makes a joke about how figuring out if an image is of a bird is virtually impossible. Now, that is not the way it is in 2025. On the right, you can see the PyTorch Torch Vision like first tutorial, which is basically training an object detection model to perform this exact task. So we've gone from virtually impossible research team in 5 years to you have just learned Python, and now you can also detect birds. How did this happen? Well, remember that the formula is data plus labels means more architectures means more capabilities. So let's start with the data. The big change in image data that happened is a combination of digital cameras and photo sharing. So in the 1980s, if you wanted to take a photo, you had to go to a store, buy film, put it in your camera, take a single photo, bring the film back to the store, they would develop it, and it would turn out really blurry. With the rise of the digital camera, and nowadays we all have cameras in our phones, photo taking became way more popular because you could just take more photos way easier. And then you could share these photos on the internet. So we've gone from, wow, it's incredibly expensive to take any photos, to now there are so many photos out there that you don't even know what to do with them. And so you have a lot of unlabeled data, but how do you create the labels? And this is probably the most famous story that I'm going to cite. But in 2009, Fei Li, along with her other collaborators, was like, well, I guess she like understood my talk 16 years before I thought of it, and like 8 years after I was born. So I was not thinking of this back then. But she had this dream that large data sets could really unlock these new capabilities. And so she pursued this idea of ImageNet, the largest image data set ever to be collected. 3.2 million labeled images, labeled across 5,000 different categories. They had to invent new ways of labeling for this to work. This was one of the first large crowdsourced image data sets. It took 19 person years to label. It was incredibly expensive. It was a leap of faith. It was orders of magnitude bigger than any data set that had ever been created before, and it paid off. 3 years after ImageNet came out, AlexNet blew away the whole competition. It was the first viable, large, deep, convolutional neural network. They had to invent new ways of using NVIDIA GPUs to even train this thing, but it just blew away the competition in this model. Nowadays, every single machine learning model that you use is a descendant of AlexNet and its results. By 2017, ImageNet was basically solved. The top performing models could perform better than the top performing human annotators. And it also introduced this idea of pre-training, the idea that you can even have a model train on ImageNet and then generalize to other domains. So you, when you want to go do your task, you don't need to collect 3 million images and labels. You can have your model learn the basic structure of an image using ImageNet and then fine-tune on whatever task that you may have later downstream with like 100 different images. This same exact story that happened in 2D imagery happened in text. Right, so the basic question is the same. How do we go from, let's say, pre-2015, if you're familiar with the concept of like the Turing test is when you have like a computer and you can't distinguish it from a human when you're like chatting with it in like a chat interface. And when I went to college, the Turing test was this like philosophical idea intended to be like, oh, can computers ever have souls? It's like a ridiculous concept to even think of like a computer that can speak English. And now, of course, you pay $20 a month and it speaks English to you. So how did this happen? So remember, unlabeled data plus labels for that data unlocks new model architectures, unlocks new capabilities. In this case, your computer could speak English or whatever other language. The unlabeled data, of course, comes from the internet. Almost all text that has ever been written by humans is online. It was written after the internet was created, because before the internet, to publish something, you had to go to a typesetter and like pound the blocks of metal into the type case and then print your thing. And after the internet, you just like type out some buttons on your keyboard and then, oh no, you've sent a horrific insult to some notorious public figure. And so these like large amounts of text were being scraped off the internet by search engines. And Gail Elbaz was like, well, I want to break the monopoly of Google on search. Let me spend a lot of money to create an open source web scrape called Common Crawl, which was intended to sort of let newcomers into the search engine space kind of compete. It did not do that. Google is still like absolutely dominant. What it did do is it created a giant source of data that people can learn from. But it was huge. It was trillions and trillions of words. And for ImageNet, you could crowdsource labeling 3 million images. You cannot crowdsource labeling 3 trillion words. It's like 1 million times bigger. And so they had to figure out how to use this unlabeled data. And they came up with the idea of like next word completion. The idea of next word completion is commonly, there's a detective model allegory for this. So if you envision sort of like you're reading a detective model, it's a murder mystery, and you read the whole novel, you go through all the details, you see all the evidence, and finally the last sentence of the novel is, the detective said the murderer is blank. Could you predict that last word? In theory, yes. You've been presented with all the evidence. You know all the characters. You should be able to predict who that last character is. But to predict that last character, you're doing a lot of reasoning. And so this idea of predicting the next word in a sentence was very important. If you could do that, then you really kind of like understood the text. And this was actually the idea that unlocked training on this unlabeled data. Unsupervised learning isn't really a thing. All that unsupervised learning is that you take the unsupervised data and then you create labels from it, and now you just have a supervised learning problem and you go train. And so the results are like, we all know this. So in 2017, the first machine learning architecture that was capable of training on like 1 trillion words, the transformer, was published. You saw pretty rapid progress over the next few years with transformer-based architectures like BERT and GPT-3. And then in 2023, ChatGPT got released, and you kind of know the rest of the story, and now it's AI, AI, AI everywhere. We're at AI after hours. You're all wearing artificially intelligent shirts. So the common theme, right, is that unlabeled data plus labels for that data makes unsolvable problems become easy, because it lets you use architectures that are bigger, more complicated, can take in that data, and will unlock new, qualitatively different capabilities. What does this look like in 3D? The physical world is in 3D. To build a great robot, you have to understand 3D. To interact with the real world, you have to understand 3D. Well, on the unlabeled data side, 3D data is going through the same sort of revolution as images did 30 years ago, with things like NeRFs and Gaussian splatting, making 3D data way more accessible to the average user than ever before. This is an incredibly detailed 3D model of Sutro Tower that was created by like an amateur drone pilot, Vincent Wu, who's also the person that did the BART video, if you ever remember the hour-and-a-half-long film of someone like riding BART. But this is all done kind of with 1 or 2 people and a single drone, and it's this incredibly detailed 3D model. So on the one hand, we're creating images, 3D models only from images. And on the other hand, if you want to use like true metric 3D, these LiDAR point cloud scanners have gotten way cheaper over the last 10 to 15 years, mainly because of all the like R&D money that's being poured in from self-driving. Like pretty significant amount of the like funding that has been raised by self-driving car companies went to basic science and research in laser physics, because the LiDARs are the most expensive component of those cars. A Waymo has like 10 LiDARs on it. And so when you're trying to drive down the cost of self-driving or like make a lot of Waymos, you have to make LiDARs way cheaper. And so as a result, LiDARs are ubiquitous now. They used to be these like really specialty things that you'd find on satellites. And now almost everyone here has a LiDAR in their phone. And so the availability of this unlabeled 3D data is exploding. Remember the formula? The other thing that we need is labeled data. Well, what do you call 3D labeled data? 3D labeled data is called a map. So whoever controls the maps will control the future. That's the last missing ingredient for 3D understanding, in what I believe, is unlabeled data plus the labels associated with it. So we have 10,000 miles of 3D data and the maps and the labels, and we're growing every year. It's our whole business model to convert this 3D data into maps. The better we do it, the more our customers use us, the more that we get. And so we end up getting this virtuous cycle at Mach 9, where our models improve the more data that they see. The more our models improve, the more accurate our results are, and the more our customers love us and use us. The more our customers love us and use us, the more data we get for them, both for training and for validation. And it's a win-win both for us and for them. Our models get more accurate, which saves them more time. And when they save more time, they use us more and we get more data. So I guess this is the obligatory come work with me slide. We are hiring. I'm going to stall here for a bit so you can all pull out your phones and scan the QR code, but this is our careers page. I'm Zach, CTO. We're kind of rapidly hiring. We're in San Francisco. And if you don't see something that you like listed there, feel free to email careers@mach9.ai or just find me after this talk. But I believe that's all I have.
Awesome. Thanks, Zach. We have some time for Q&A. We have 5-ish minutes for Q&A. If anyone have questions, I can run the mic.
I'll put the QR slide.
Oh, okay. Perfect.
So you did mention Feifei. What do you make of Feifei's trajectory for a company, World Labs? Do you consider them to be a competitor? Do you consider them to be, a partner?
I think what World Labs is doing is really cool. They don't currently have a product that competes with our product in any way. They tend to concentrate more on these sort of image-based understanding methods. We concentrate more on LiDAR. I could imagine that in 5 years we'll be competitors as we kind of converge towards the same point, but we're not really interacting right now.
Sorry, I work in this space. Really quick, what do you make of, it isn't all just drawing lines on the ground and then making spatial reasoning of maps. There's a lot of labeling of what makes sense, for example, for like a car in a scene. That's called motion planning, right? Will that be a domain that you step into, or is this something, and you kind of described it as only map making. Is there another step after map making?
Yeah, definitely. And I mean, my background is actually in autonomous driving motion planning. That's what I was doing before Mach 9. And I think that there's like a huge planning problem as well. If you're dealing with this very uncertain data, planning under uncertainty is incredibly hard. But what we found is sort of a lot of planning problems, especially in self-driving when I was working on it, were tied back to semantic understanding. Like, how do you deal with, oh no, my vision system says that the lane went away for a second, but I don't want to slam on the brakes. And so they're very sort of closely related. You can solve problems in one domain by solving problems in the other.
Hi, thanks a lot. So I wonder if you could expand a little bit on how you think about the user experience and specifically your persona or your user, and how you kind of design the user experience of the maps. Are there any design principles that you decided to go with in order to form that kind of vision?
Yeah, absolutely. So right now, we can't guarantee 100% accuracy, but our customers need 100% accuracy. So the persona that we designed for is for the idea of sort of a quality assurance person, an actual land surveyor that's going in and making sure that we're accurate and doing spot corrections if we're not. And we very heavily design with that. We have a lot of sort of contextual inquiries. Because we operate in such a high-value enterprise space, we know our customers personally. We get lunch with them. We talk to them on calls. And we're very closely connected. And there's a whole other sort of side of Mach 9 that isn't related to machine learning that I didn't talk about at the IA After Hours event, but that involves this in-browser 3D CAD viewer experience.
Any other question? Last call. All right. Thank you, Zach.
Thank you.